Welcome to this first lecture in a series of lectures for the course titled Algebraic Curves and Riemann Surfaces. So let me quickly tell you to begin with what the goals of the present lecture are. So in this lecture we will first try to understand the idea of a Riemann surface. And second, we will try to look at some examples. So before we begin, let me try to recollect some basic ideas from complex analysis, that is functions of one complex variable. Okay, so we look at a function. So here is the complex plane which we call as a Z plane, and suppose we have an open set U in the complex plane, and we have a function f which is defined on this open set U. You can think of U as the interior of this amoeba like region that I have drawn here, and the function takes complex values again. So there is another copy of the complex plane, and we call this the omega plane, where omega is the variable is the image of the variable z under f. Of course this is the origin on both planes, and this is the real axis, this is the imaginary axis, and likewise we here have the real axis and we have the imaginary axis. And the idea is to recall what it means for a function to be holomorphic or analytic at a point z0 in this open set U. So recall that f of z is said to be analytic or holomorphic at z0 if one of the following three equivalent conditions holds. So the first condition is that if you write omega as u plus iv, so that u becomes the real part of f and v becomes the imaginary part of f, then we want that the first partial derivatives ux, which is dou u by dou x, the first partial derivative of u with respect to x, and then uy similarly dou u by dou y, and then vx dou v by dou x, vy is dou v by dou y, exist and are continuous, and further satisfy the Cauchy-Riemann equations ux is equal to Vy and Vx is equal to minus Uy for all z in a neighborhood of the point z0. So this is one condition that would define f to be analytic or holomorphic at the point z0. Okay, there are and usually this is the condition that you come across in a first course in complex analysis, which I think all of you have done. The next condition that is used to define the holomorphicity or analyticity of a function at a point is the usual definition, the down to earth definition that the function is differentiable not only at that point but at every point in a neighborhood of that point. So it's a straightforward definition. So that's what I'm going to write down as the second definition. The limit as delta z tends to 0 of f of z plus delta z minus f of z by delta z exists for every point z in a neighborhood of z0. So this is the condition that the function is not only differentiable at that point but it is also differentiable at every point in a neighborhood of that point. And then the third condition, which is a condition which is also often adopted, is that the function is represented by a convergent power series in a neighborhood of the given point z0. So let me write that down. There exists a power series of the form sigma n greater than or equal to 0 an z minus z0 to the power of n, which is convergent to f of z for each point z in a neighborhood of z0. So these are the three equivalent definitions of a function being analytic or holomorphic at a point. Now let me make some remarks about these definitions. The connection between 1 and 2 is that the derivative can be expressed in terms of u and v. Okay, so let me write that formula down. The connection between 1 and 2 is the derivative of f is just the partial derivative of f with respect to x, namely it is ux plus ivx. Okay, and the connection between 2 and 3 is what I would call as most spectacular. It's this amazing thing which says that if a function is differentiable not only at a point but in a neighborhood of that point, then the function is actually infinitely differentiable. That is because you see, you would have studied that a power series, a convergent power series, if you it allows you to differentiate it term by term, and the differentiated series also is a convergent power series with the same radius of convergence. And since you can do this ad infinitum, it amounts to saying that a convergent power series is infinitely differentiable, and requiring that such a convergent power series converges pointwise to the function f of z also therefore requires that f is infinitely differentiable. So what is spectacular about that 2 and 3 are equivalent is this amazing fact that differentiability once at all points in a neighbourhood of a given point gives you infinite differentiability for all points in a neighbourhood of that point, okay. And this is something that I hope all of you would have realized when you did a first course in complex analysis, that is the major distinguishing feature between functions of one real variable and functions of one complex variable, okay. So the connection between the ANs is that they are actually the Taylor coefficients. So let me write that down. The connection between, so let me write it properly, 2 and 3 is, so the first thing is once differentiable in a neighbourhood implies infinitely differentiable in a neighbourhood and then the next thing is that ANs are actually given by the nth derivative of f at z0 by factorial n, okay, where the nth derivative of f is just differentiating f n times with respect to z, so that this power series to which converges to f is nothing but the Taylor expansion of the function f around the point z0, okay. It is just the Taylor expansion so this is just to recall the idea of an analytic function. So we will proceed to some further properties of analytic functions, which I will require in the sequel. Okay, now I also want to recall another important fact, which is the following. So recall again, an injective holomorphic map is a holomorphic isomorphism. So this is again a deep fact. So if you have a holomorphic map, say f is a holomorphic map from U to C, where U is an open subset, okay, and if f is holomorphic on U and f is injective, that is if f is holomorphic and f is injective, then f of U is open, okay. In fact, f is what is called an open map. It will take open sets to open sets, okay, and since f from U to fu is a bijective map, you can make sense of the set theoretic inverse from fu to U, and it is a deep fact that that set theoretic inverse is also holomorphic, okay, and f inverse from f of U to U is also holomorphic. So therefore the important thing about this is that if you have a holomorphic map and you know that it is injective, okay, then you do not have to put the extra condition that the image of the open set on which it is defined is open, okay, that comes automatically because it is an open map, which means it takes open sets to open sets. And you also have the condition that the inverse map is not only continuous, it is actually holomorphic. So what this tells you is that whenever you have an injective holomorphic map, that is actually giving you a holomorphic isomorphism with the image of the source with the image, okay. So this is another thing that we would use. Alright, so now let us try to go and try to understand the idea of a Riemann surface, okay. So let me rub this off. So the idea of a Riemann surface. So what I am thinking of to begin with, so that we are down to earth and we have a concrete grasp of the kind of ideas that we want to formulate, is the following. So we start with the surface, say like the sphere, or torus or cylinder that you can visualize in 3 space, okay. We start with the surface, okay. So let me draw pictures of these. So here is the sphere S2, and then here is a torus which we call as T1, and then you can also think of a cylinder. Of course this I'll make this dotted line so that I just want you to understand that this is not the boundary of the cylinder, but this is an infinite cylinder, okay. So these are all surfaces that you can imagine in 3 space, and more generally you can also imagine some surface like this in 3 space, more generally any surface like this. And what is it that I want to do? It is the following. Suppose I'm given a point x0 on that surface, okay, and suppose I am given a small neighborhood of that point which looks like a disk, okay. So I can think of a similar situation on each of these surfaces. I have a point x0 and a small disk surrounding it. So when I say a small disk surrounding it, the disk is not flat, because the surface is curved, so it is some kind of a curved disk, but topologically you can flatten it and think of it as a disk in the complex plane. So when I say I have a point and a disk like neighborhood surrounding it, I mean that there is a small neighborhood surrounding the point which topologically looks like a disk in the complex plane, okay. And well, on a general surface also, here is my point and here is my disk, a disk like neighborhood, okay. And suppose that so let me call this more generally as x. So x could be any one of the 3, okay, or even other things that you can think of. And what is it that I want to do? So suppose you are given, so from D to C, suppose you are given a function f from this disk like neighborhood to C, okay. So it's a complex valued function, okay. So I have a surface, I have a point on the surface, and I have a small disk like neighbourhood D, and I have a function, right, and this function is defined for every point on this disk, which means it is also defined at x0, and this function takes complex values. And what is it that I want to do? What I want to do is I want to formulate a definition by giving a set of conditions as to when the function f is holomorphic at the point z0, at the point x0. Okay, so we want to define when f is holomorphic at x0. This is what you want to do. Okay, so this is the point. I have a surface, I have a point, and I have a small disk surrounding that point, a disk like neighbourhood surrounding that point, and I have a function which is defined on this disk, and I want to say, I want to be able to say in a nice way, in a clear way, without any ambiguity, when the function f is holomorphic at that point x0. So what is it that I want? I want to actually do the complex analysis that I do on the plane. Okay, I want to do that same kind of complex analysis, I want to do that on a surface. Okay, so I want to be able to do complex analysis on a sphere or on a torus or on a cylinder, wherever it is possible. Okay, that is the whole idea, and and it is because of this that Riemann surfaces are being considered. Okay, so the main use of Riemann surfaces, the idea of a Riemann surface is to be able to do complex analysis on a surface. Okay, so well, how do you define f to be holomorphic at x0? Okay, or more generally, how do you define f to be holomorphic at every point on D if you want? How do you do that? There is a very easy way of doing it in the following sense, which is also very natural, very intuitive. It is the following. So what we do, one way to do this is to identify D with an open subset, say the unit disk delta, namely the set of all complex numbers with modulus 1, modulus less than 1. This is open unit disk, by choosing a homeomorphism and by the way, let me remind you that a homeomorphism is a topological isomorphism. Okay, topological isomorphism. Phi from D to delta. So you see, so I have my D here, which is sitting inside the surface, okay, and which contains the point x0, and I have this function f which is defined on D and which is taking complex values, and my aim is to be able to say that f is holomorphic at a point of D. Okay, so what I do is I take an isomorphism, topological isomorphism phi from D into the unit disk in the complex plane. So this is a subset of C, and then I take this composition. What is this composition? This is, first I apply phi inverse, which is correct because phi is a topological isomorphism, so phi inverse is also a continuous map. Phi inverse is also in fact a topological isomorphism, so I apply phi inverse and then I compose it with f. So I get a map from the unit disk in the complex plane to complex numbers. So it is a function from an open subset of the complex plane taking complex values, and for such a function it is very easy to define when it is holomorphic at a point. So what I do is that I require that this function is holomorphic at the point here, which is the image of the point x0, okay. So and requiring that f circle phi inverse is holomorphic at phi of x0, okay. So I've just used the intuitive idea that the neighborhood of the point that I've been given on the surface really looks like a disk. So I identify that neighborhood with a disk in the complex, say the unit disk in the complex plane, and then using this identification I am able to get a function from that disk in the complex plane into the complex numbers, for which it is easy for me to say when it is holomorphic at a point, okay. So it is a very intuitive definition. So this a pair like this, a pair in fact let me also say that I can now say I can extend this definition not only to the point x0 of D, but I can extend it to all points of D. So I can say f is holomorphic on D if f circle phi inverse is holomorphic on delta, because that way I have covered every point of D. So you see in the same way we may say that f is holomorphic on D if f circle phi inverse is holomorphic on delta, okay. So therefore you see what you can understand is that this choice of this identification phi of this disk like neighborhood with a real disk, okay, this identification and this disk like neighborhood is a pair of data which is what is called a chart. It is called a complex coordinate chart, okay. So the pair D comma phi is called a complex coordinate chart. So I am now starting with a very intuitive point of view that a Riemann surface comes up as trying to be able to do complex analysis on surfaces that we see in everyday life, the surfaces that you can really imagine concretely, okay. So I am starting with that intuitive definition. So for the moment my surface x is, I have not defined what a surface x is formally, but I will do that formally in the succeeding lectures, okay. For the moment I am taking something very concrete that you can really see, okay. So well, a pair like this is called a complex coordinate chart, and it is called a complex coordinate chart because it allows you to do complex analysis on this disk D, this disk like neighborhood D on the surface. So you see so that is the purpose of a coordinate chart, okay. A coordinate chart provides you with a coordinate, okay, with which you can do complex analysis. So the idea is that if you call a varying point here as x, then you can call a varying point here which is in the image, which is in its image under phi as z. So you have z is equal to phi of x, okay, and this z is actually a coordinate on this complex plane, okay. So what you have done is that you have somehow tried to give a position, a unique position to every point on this disk D, disk like neighborhood D. Okay, you're provided it with a different symbol, okay, in a continuous, in a continuously isomorphic way, which is a complex variable, so that the resulting function becomes a function of one complex variable, a function which is defined concretely on an open subset of the complex plane, for which you can do complex analysis. Okay, so more generally, what is a complex coordinate chart? More generally, I needn't have taken here a disk like neighborhood. I could have taken just any open set containing the point, and then I would have to choose again a topological isomorphism of that open set with an open set in the complex plane. Okay, so more generally, what is a complex coordinate chart? More generally, a complex coordinate chart is a pair u comma phi, where u is an open subset of X, phi from u to v is a homeomorphism of u onto an open subset V of the complex plane. Okay, so this is what a coordinate chart is. Okay, and you can now see that somehow so the more general diagram will look like this. So I have this point X, say X naught, and then I have some open set Q on the surface, and I have an identification of this by a homeomorphism, a topological isomorphism of this with the subset of the complex plane. So here is my subset of the complex plane V. Okay, and this is a chart. Okay, this pair consisting of u and phi is a chart. And why is it useful? It's useful because whenever I have a function f defined on u taking values in C, I can call f to be holomorphic if the composite function, which is given by phi inverse followed by f, is holomorphic. Okay, so I chose to begin with a disk because it's intuitive, but then instead of a disk I could have had an open set, right? Fine. So at this moment it would appear that we could take for our definition of a Riemann surface just a surface that we can imagine in 3 space, and which is equipped with a set of charts like this, such that these charts cover all of X. That means basically I want to do complex analysis on the Riemann surface. So given any point on the Riemann surface, it should be contained in a chart, it should be contained in the U member of a chart, so that I can use that chart to do complex analysis in that neighborhood of that point. So this could be taken as the working definition or the first definition. Okay, so let me write that down, but let me also caution you that we will run into problems very soon, and that will tell you how the definition has to be modified. So let me write this down. So preliminary definition of a Riemann surface is a surface X covered by a collection of charts u alpha phi alpha, where alpha runs over some indexing set. So this capital I is an indexing set, and for each element in I have a chart u alpha comma phi of alpha, and these u alphas should cover X. Okay, so let me write that down. X is equal to union over alpha u alpha. Okay, this ensures that at every point of X I can really do complex analysis, okay, using the chart that is available at that point. But we immediately run into problems. What is the problem that we will run into? It's a kind of it's the following kind of obvious problem, namely, given a point it might occur in more than one chart. Okay, so let's look at this situation, but we run into problems. As follows. Suppose u alpha 1 and u alpha 2 both contain the point x naught. Okay, so let us look at this situation. So I have, so let me draw a diagram. I would need a larger diagram, so let me go back here. So here is my surface, and I have one open set u alpha 1, and it is equipped with a chart, namely I have a phi alpha 1, which is a homeomorphism of u alpha 1 with some subset of the complex plane, which I will call as v alpha 1. Okay, and well, on the other hand, my point x naught also lies in another open set, which is u alpha 2, which is the first member of a chart. So there is again another homeomorphism phi alpha 2, which identifies this u alpha 2 with another open set, let me call that as v alpha 2 in the complex plane. Okay, so this is my situation, and suppose that I have a function f that is defined on this intersection. Okay, so suppose so let me write that there. Consider a function f from u alpha 1 intersection u alpha 2 to C. Suppose you have a function is defined on that intersection. So in particular you could have considered a function is defined in a neighborhood of the point x naught, okay, and you could consider a small enough neighborhood so that it is in the intersection, right. And the difficulty we will run into is that is the following. It's in trying to decide whether the function is holomorphic at x naught or not. The reason is because we have two ways of defining f to be holomorphic at x naught. Okay, so there is one way of saying that f is holomorphic at x naught is to say that this composition namely which is f circle phi alpha 1 inverse, this composition is holomorphic at the image of x naught under this map. Okay, so if you want, I will call that as z1. Okay, and so z1 is phi alpha 1 of x naught, and well the other way of deciding that f is holomorphic at x naught is to require that this composition, which is f now followed by which is now phi alpha 2 inverse followed by f, is holomorphic at the point z2 where Z2 is the image of x0 under phi alpha 2. Okay. So you see, so let me write that down clearly. F is holomorphic at x0 according to the chart u alpha 1 phi alpha 1 if F circle phi alpha 1 inverse is holomorphic at Z1 and according to u alpha 2 comma phi alpha 2 if F circle phi alpha 2 inverse is holomorphic at Z2. So you get two definitions of F being holomorphic at the point x0. That is because you have chosen two charts which are available around the point, and in fact you could have an infinite collection of charts, and then that would give you an infinite set of definitions for F being holomorphic at the point x0. Clearly this is not something that we want, because you know that the idea of holomorphicity, or for that matter any property of a function, has to be intrinsic to the function. It should not be a property that should be ambiguously defined. Okay. All good properties of functions like continuity, differentiability, analyticity or holomorphicity, these should be intrinsic properties of functions. Okay. They should be properties which do not depend on let me say reparameterization. Okay. Because after all what these charts are doing are just reparameterizing that neighborhood, a neighborhood around that point in terms of complex variables. Okay. So what we really do not want to happen is that, for example, that F circle phi alpha 1 inverse is actually holomorphic at Z0, but F circle phi alpha 2 inverse is not holomorphic at Z1 at Z2. Okay. Okay. What should not happen is that one of these is true and the others are false, the other is false. Okay. Such a thing should not happen. Okay. So how do you remedy this situation? You remedy the situation in the following way. You see, I have this kind of a situation where I do not want the function to be holomorphic with respect to one chart at a point, and it is not holomorphic with respect to some other chart. Okay. So how do I avoid this? So you see, it should be same to require the holomorphicity using any chart. So this is what the ideal situation is, that no matter what chart you use, the idea of a function being holomorphic at a point should be unambiguous, because holomorphicity is an intrinsic property. It should be an intrinsic property of a function. Okay. Okay. Because holomorphicity should be an intrinsic property of a function. Okay. So let me repeat, it should not be that because I have different charts my definition of holomorphicity depends on the chart. If I change the chart, the holomorphicity is false, and for some other chart the holomorphicity is true. I do not want such a thing to happen. So this tells you that the charts have to be compatible in a certain sense. And how do you get this compatibility? So you get this compatibility in the following way. You see, to ensure that the above happens, we require the following. So let me first explain it using the diagram here. So you see I have this shaded region here. This shaded region here is u alpha 1 intersection u alpha 2 is the shaded region here, and that's of course it's an intersection of two open sets, so it's open. It's an open subset of u alpha 1, and since phi alpha 1 is a homeomorphism, the image of this here is going to be an open set in v alpha 1. Okay, so I will get an open set here which I would call as v alpha 1 2, and v alpha 1 2 is nothing but is just the image under phi alpha 1 of u alpha 1 intersection u alpha 2. Okay, and similarly so this shaded region goes to this shaded region here, and similarly this open set u alpha 1 intersection u alpha 2 goes to another shaded region that I draw here, which is again an open subset of v alpha 2, which I would like to call as v alpha 2 1. Okay, so v alpha 2 1 is phi alpha 2, the image under phi alpha 2 of u alpha 1 intersection u alpha 2. Okay, and now what I want you to understand is to look at this map. So I look at this map from this shaded region to this shaded region, okay, from this open set v alpha 1 2 to this open set v alpha 2 1, and how do I get this map? I first take phi alpha 1, I take so let me just for convention let me change the direction of the map. So I first take phi alpha 2 inverse. Phi alpha 2 inverse will take this shaded region which is v alpha 2 1 into u alpha 1 intersection u alpha 2, and then I apply phi alpha 1. Okay, so actually I have a map from this shaded region to that shaded region. Okay, so I call that map as G12. So what is this G12? So G12 is first apply phi alpha 2 inverse restricted to v alpha 2 1. Okay, that will take v alpha 2 1 to homeomorphically onto u alpha 1 intersection u alpha 2, and then apply phi alpha 1 restricted to u alpha 1 intersection u alpha 2. Okay, so I will compose this with phi alpha 1 restricted to u alpha 1 intersection u alpha 2. Okay, so it will go from v alpha 2 1 to v alpha 1 2. Okay, and you can see that this is a composition of homeomorphisms. So this is a homeomorphism. Okay, it's a homeomorphism. This is a homeomorphism because the restriction of a homeomorphism to an open set is also a homeomorphism. Okay, and a composition of homeomorphisms is again a homeomorphism. So this is a homeomorphism, and what is it a homeomorphism of? It's a homeomorphism of two open subsets of the complex plane. Okay, so I can require that to be holomorphic. Okay, okay, so require the following homeomorphism G12 to be holomorphic. After all, it's a homeomorphism. Basically it's a mapping from an open subset of the complex plane to another open subset of the complex plane. I just want it to be homeomorphic, I just want it to be holomorphic, but the point is it's already a homeomorphism, which means it's already injective. So you see by a remark that I told you earlier, it's an injective holomorphic map, so it's a holomorphic isomorphism. So what it will tell you is that it will tell you that G12 is not only is G12 holomorphic, but G12 is an open map and its inverse is also holomorphic. So G12 inverse is also holomorphic. Okay, so putting this condition helps us, it makes sure that you don't get a conflict in these two definitions. And why is that so? It's because of the following simple observation. So let me write that down. So requiring G12 to be holomorphic would also make it into a holomorphic isomorphism by a remark that I recalled some time ago at the beginning. Okay, and now why does this help? Why does this condition help? It helps because of the following reason. Because you see, F circle phi alpha 1 inverse, okay, if I compose it with G12, okay, I get F circle phi alpha 2 inverse. See, because if I do not worry about writing these restrictions, which is a little cumbersome, okay, I just write this as phi alpha 1 circle phi alpha 2 inverse with the meanings as to where these maps are being taken understood. Then I just write G12 as phi alpha 1 circle phi alpha 2 inverse, and then, you know, so if I here instead of G12, if I plug in a phi alpha 1 circle phi alpha 2 inverse, then you see I get F circle phi alpha 2 inverse, and you see that therefore this map and this map, they differ by holomorphic isomorphism, and therefore this is holomorphic if and only if that is holomorphic, okay, because G12 has an inverse. If this is homomorphic, G12 is already holomorphic, and this is a composition of holomorphic maps, so that is holomorphic, and conversely if that is holomorphic, I can multiply on the right by G12 inverse to get that this is holomorphic, okay. So the above equation tells us that F circle phi alpha 1 inverse is holomorphic if and only if F circle phi alpha 2 inverse is. So there is really no conflict in using these two charts to define holomorphicity, and now if you require this condition to happen whenever you have two intersecting charts, okay, in which case we say that those two charts are pairwise compatible, then you are in a good situation. So so we make this requirement that not only is the Riemann surface just a bunch of is a surface which is covered by a collection of charts, but these charts whenever they intersect, on the intersection these functions G12s, okay, which are called the transition functions, these are called transition functions, and we want these transition functions to actually be holomorphic, okay. So let me write that down, and that gives us a very concrete first definition of a Riemann surface, okay. So let me write that down. So if we require that functions such as G12 called transition functions to be holomorphic, whenever u alpha 1 intersection u alpha 2 is non-empty, we get a compatible collection of charts which gives a Riemann surface structure on X, okay. So let me again repeat that. So we started with trying to do complex analysis on a surface, and we realized that we could do that if we had these complex coordinate charts, and we want to be able to do that at every point, so these charts should cover the whole surface. But then we run into problems deciding whether a function is holomorphic at a point, because there may be more than one chart available at that point, and in order that such ambiguity does not arise, we put this extra condition that for any two intersecting charts the transition function is holomorphic, and once you do that everything is fine. So you just take a collection of charts which are compatible with each other, okay, this is the compatibility condition, and that gives you a Riemann surface structure on X, okay. So this is the beginning definition of what a Riemann surface is, okay. So let me stop here.